if all atoms were unique, you couldn't have macaroni and cheese.
How would we survive?
Life would be hard. Yeah. All right, where was I?
You have like 2 pages left of that thing.
Yeah, okay, here it is. So, there are often great distances between the detailed laws and the main aspects of a real phenomena. For example, if you watch a glacier from a distance and see the big rocks falling into the sea and the way the ice moves and so forth.
You'd have to have a giant beard.
Yes. It is not really essential to remember that it is made out of little hexagonal ice crystals. Yet, if understood well enough, the motion of the glacier is, in fact, a consequence of the character of these hexagonal ice crystals. But it takes quite a while to understand all of the behavior of the glacier. In fact, nobody knows enough about ice yet, no matter how much they've studied the crystal. However, the hope is that if we do understand the ice crystal, we shall ultimately understand the glacier. In fact, although we've been talking in these lectures about the fundamentals or the fundaments of the physical laws, I must say immediately that one does not, by knowing all of the fundamental laws as we know them today, immediately obtain an understanding of anything much. It takes a while, and even then it is only partial. Nature, as a matter of fact, seems to be so designed that the most important things in the real world appear to be a kind of complicated accidental result of a lot of laws. To give an example, nuclei, which involve several nuclear particles, protons and neutrons, are very complicated. They have what we call energy levels, and they can sit in states or conditions of different energy values, and various nuclei have various energy levels. And it's a complicated mathematical problem which we can only partly solve to find the position of the energy levels. The exact position of the levels is obviously a consequence of an enormous complexity, and therefore there is no particular mystery about the fact that nitrogen, with 15 particles inside, happens to have a level of 2.4 million volts, and another level at 7.1, and so on. But the remarkable thing about nature is that the whole universe, in its character, depends on precisely the position of one particular level in one particular nucleus. In the carbon-12 nucleus, it so happens there is a level at 7.82 million volts, and that makes all the difference in the world. So the situation is the following. If we start with hydrogen, and it appears that at the beginning the world was practically all hydrogen, then as the hydrogen comes together under gravity and gets hotter, nuclear reactions can take place, and it can form helium, and then the helium can combine only partially with the hydrogen and produce a few more elements a little heavier. But these heavier elements disintegrate right away back into helium. Therefore, for a while there was a great mystery about where all the other elements in the world came from, because starting with hydrogen, the cooking process inside of stars would not make much more than helium and less than half a dozen other elements. Faced with this problem, Professors Hoyle and Salpeter said that there was one way out.
Saltpeter?
It's S-A-L. It looks like saltpeter, but there's no T.
Oh.
So Salpeter? I don't know.
Oh, saltpeter.
Yeah. If 3 helium atoms could come together to form a carbon, we can easily calculate how often that should happen in a star. And it turns out that it should never happen except for one possible accident. If there happened to be an energy level at 7.82 million volts in carbon, then the 3 helium atoms could come together, and before they came apart, they would stay together for a little longer on average than they would do if there were no level at 7.82. And staying there a little longer, there would be enough time for something else to happen and to make other elements. If there was a level at 7.82 million volts in carbon, then we could understand where all the other elements in the periodic table came from. And so, by a backhanded, upside-down argument, it was predicted that there is in carbon a level at 7.82 million volts, and experiments in the laboratory showed that indeed there is. Therefore, the existence in all the world of all these other elements is very closely related to the fact that there is this particular level in carbon. But the position of this particular level in carbon seems to us, knowing the physical laws, to be a very complicated accident of 12 complicated particles interacting. This example is an excellent illustration of the fact that an understanding of the physical laws does not necessarily give you an understanding of things of significance in the world in any direct way. The details of real experience are often very far from the fundamental laws. We have a way of discussing the world when we talk of it at various hierarchies or levels, Now, I do not mean to be very precise, dividing the world into definite levels, but I will indicate by describing a set of ideas what I mean by hierarchies of ideas. For example, at one end we have the fundamental laws of physics. Then we invent other terms for concepts which are approximate, which have, we believe, their ultimate explanation in terms of the fundamental laws. For instance, heat. Heat is supposed to be jiggling, and the word for hot, a hot thing, is just the word for a mass of atoms which are jiggling. But for a while, if we are talking about heat, we sometimes forget about the atoms jiggling, just as when we talk about the glacier, we do not always think of the hexagonal ice and the snowflakes which originally fell. Another example of the same thing is a salt crystal. Looked at fundamentally, it is a lot of protons, neutrons, and electrons, but we have this concept of salt crystal, which carries a whole pattern already of fundamental interactions. An idea like pressure is the same. Now, if we go up higher from this, in another level, we have properties of substances like refractive index, how light is bent when it goes through something, or surface tension, the fact that water tends to pull itself together, both of which are described by numbers. I remind you that we have to go through several laws down to find out that it is the pull of atoms and so on. But still, we say surface tension, and do not always worry, when discussing surface tension, about the inner workings. On up in the hierarchy, with water we have waves, and we have a thing like a storm, and the word storm, which represents an enormous mass of phenomena, or a sunspot or star, which is an accumulation of things. And it is not worthwhile always to think of it all the way back. In fact, we cannot, because the higher up we go, the more steps we have in between, each one of which is a little weak. We have not thought them all through yet. As we go up in this hierarchy of complexity, we get to things like muscle twitches or nerve impulses, which is an enormously complicated thing in the physical world, involving an organization of matter in a very elaborate complexity. And then come things like frog.
Yes.
Yes. Frog. And then we go on and we come to words and concepts like man and history or political expediency and so forth, a series of concepts which we use to understand things at an even higher level. And going on, we come to things like evil and beauty and hope. So which end is nearer to God, if I may use a religious metaphor? Beauty and hope, or the fundamental laws? I think that the right way, of course, is to say that what we have to look at is the whole structural interconnection of the thing, and that all the sciences, and not just the sciences, but all the efforts of intellectual kinds are an endeavor to see the connections of the hierarchies, to connect beauty to history, to connect history to man's psychology, and man's psychology to the working of the brain, and the brain to the neural impulse, and the neural impulse to the chemistry, and so forth, up and down, both ways. And today we cannot, and it is no use making believe that we can, draw carefully a line all the way from one end of this thing to the other, because we have only just begun to see that there is this relative hierarchy. And I do not think that either end is nearer to God. To stand at either end and to walk off that end of the pier only, hoping that out in that direction is the complete understanding, is a mistake. And to stand with evil and beauty and hope, or to stand with the fundamental laws, hoping that way to get a deep understanding of the whole world with that aspect alone, is a mistake. It is not sensible for the ones who specialize at one end and the ones who specialize at the other end to have such disregard for each other. They don't actually, but people say that they do. The great mass of workers in between, connecting one step to another, are improving all of the time our understanding of the world, both from working at the ends and working in the middle, and in that way we are gradually understanding this tremendous world of interconnecting hierarchies.
That's really awesome.
Yeah.
I love that.
Great way to end that lecture. Okay. Lecture 6, Probability and Uncertainty, the Quantum Mechanical View of Nature. So, at the break, you heard Feynman speaking the beginning of this lecture. So I'll start from part of that here. He says, one odd characteristic is that they often seem to become more and more unreasonable, they being these phenomena. They become more and more unreasonable and more intuitively far from obvious. To take an example, in the relativity theory, the proposition is that if you think two things occur at the same time, that is just your opinion. Someone else could conclude that of those events, one was before the other, and that therefore simultaneity is merely a subjective impression. So when I read this, I was thinking, like last episode, I got this wrong about because I gave the example of two stars going nova. And that depending on where you are, you may think that they appear to take place thousands of years apart, but if you're in a different place, they might look like they happen at the same time. So what I think, based on what he just said here, that what I was getting wrong was starting out saying that they happen at the same time and saying that depending on your perspective, you would see them taking place at different. What he's saying is your perspective is what matters, I think is what he's saying here.
Yeah.
So it's just a strange way to look at it, but it's like that thing that you were just reading about in the first segment about this fast radio burst that is in a galaxy billions of light years away from us. Did it just happen? Is that basically what he's saying? Like it?
No, I think what he's saying is that because the laws are locally conserved, you have to use your perspective to make any sense out of it.
Right.
You can't say, well, that person saw them happen at different times. Right?
Yeah.
So let me work from that angle because you're not there and moving and whatever. You see what I
okay.
mean?
Yeah. Okay.
You have to figure it out from your perspective.
Yeah.
Because that's what's the laws are conserved locally.
Yeah. Yep. He says, if you think two things occur at the same time, that's just like your opinion.
Yeah,
man.
yeah. That's right.
Someone else could conclude that of those events, one was before the other.
Right.
It's just your opinion, man. There is no reason why we should expect things to be otherwise, because the things of everyday experience involve large numbers of particles, or involve things moving very slowly, or involve other conditions that are special and represent, in fact, a limited experience with nature. It is a small section only of natural phenomena that one gets from direct experience. It is only through refined measurements and careful experimentation that we can have a wider vision. And then we see unexpected things. We see things that are far from what we would guess, far from what we could have imagined. Our imagination is stretched to the utmost, not as in fiction to imagine things which are not really there, but just to comprehend those things which are there. It is this kind of situation that I want to discuss. So let us start with the history of light. At first, light was assumed to behave very much like a shower of particles, like rain or like bullets from a gun. Then, with further research, it was clear that this was not right, and that the light actually behaved like waves, like water waves, for instance. Then, in the 20th century, on further research, it appeared again that light actually behaved in many ways like particles. In the photoelectric effect, you could count these particles, and they are called photons now. Electrons, when they were first discovered, behaved exactly like particles or bullets, very simply. Further research showed from electron diffraction experiments, for example, that they behaved like waves. As time went on, there was a growing confusion about how these things really behaved. Are they waves or particles? Particles or waves? Everything looked like both. This growing confusion was resolved in 1925 or 1926 with the advent of the correct equations for quantum mechanics. Now we know how the electrons in light behave, but what can I call it? If I say they behave like particles, I give the wrong impression. Also, if I say they behave like waves, they behave in their own way, which technically could be called a quantum mechanical way. They behave in a way that is like nothing that you have ever seen before. Your experience with things that you have seen before is incomplete. The behavior of things on a very tiny scale is simply different. An atom does not behave like a weight hanging on a string and oscillating, nor does it behave like a miniature representation of the solar system with little planets going around in orbits, nor does it appear to be somewhat like a cloud or a fog or of some sort surrounding the nucleus. It behaves like nothing you have ever seen before. There is one simplification, at least. Electrons behave in this respect in exactly the same way as photons. They are both screwy, but exactly in the same way. How they behave, therefore, takes a great deal of imagination to appreciate, because we are going to describe something which is different from anything you know about. In that respect, at least, this is perhaps the most difficult lecture of the series, in the sense that it is abstract, in the sense that it is not close to experience. I cannot avoid that. Were I to give a series of lectures on the character of physical law, and to leave out from this series the description of the actual behavior of particles on a small scale, I would certainly not be doing the job. This thing is completely characteristic of all of the particles of nature and of a universal character, So if you want to hear about the character of physical law, it is essential to talk about this particular aspect. It will be difficult,